Fine. Let's start. Number 10. The flyby anomaly. Here's something they don't put in the press releases. When we send a spacecraft to the outer solar system, we don't just point it and fire. We can't. We don't have rockets big enough. So we cheat. We swing the probe past a planet, close and fast, and we steal a little of that planet's motion to fling the craft onward. It's called a gravity assist, and it is one of the most elegant tricks in all of spaceflight. We've done it dozens of times. We know the math down to the millimeter. Except, on a handful of occasions, the math didn't close. On the 8th of December, 1990, a probe called Galileo came screaming past Earth to pick up speed on its way to Jupiter. The engineers at the Jet Propulsion Laboratory tracked it the way they always do, by listening to the precise pitch of its radio signal, which shifts as the craft speeds up or slows down. They knew exactly how fast Galileo should be going when it came out the far side of the flyby. And when they checked the numbers, the probe was moving too fast. Not by much. By about 4 millimeters per second. Roughly the speed a snail moves. But it was there, and it shouldn't have been. At first you shrug. A rounding error. A bad measurement. Space is messy, but then it happened again. In 1998, a probe called Near Shoemaker did its own Earth flyby, and it came out the other side, carrying an extra 13 millimeters per second. Then, Cassini, on its way to Saturn, picked up a couple of millimeters it wasn't owed. Then, Rosetta, the comet chaser, did it too. Different spacecraft. Different years. Different teams. The same little ghost in the numbers. So in 2001, two physicists at JPL, John Anderson and James Williams, sat down with all the tracking data and went looking for the pattern. And here's the part that gets under your skin. There was a pattern. The size of the extra speed depended on the angle of the flyby, specifically on how the spacecraft came in and went out relative to Earth's equator. Anderson even wrote down a little formula that predicted the kick. A formula for an effect that, according to known physics, should not exist. They checked everything. The pull of the oceans, the faint drag of the upper atmosphere, the pressure of sunlight, the subtle warping of space that Einstein predicts. They audited it all, line by line, and none of it explained the extra speed. The probe just gained energy out of nowhere, took its little snail's pace bonus, and carried on into the dark. Now, I want to be honest with you, the way a friend would. Most physicists do not think this is new physics. The leading guess is that there's some boring, conventional effect we just haven't modeled right yet. A subtle wrinkle in the map of Earth's gravity. A quirk in how the tracking stations talk to each other. And tellingly, some later flybys showed no anomaly at all, which is a strong hint that whatever it isn't a universal new force of nature. But here's the thing. Decades later, the formula still sits there, describing an effect nobody has fully derived. We've flung our own machines past our own planet, watched them come back wrong, and we still can't say exactly why. It's a small mystery, millimeters per second. But it's ours, measured in our own backyard, on hardware we built with our own hands. And space is supposed to be the place where the math always closes. Sometimes it just doesn't. Number 9. The Pioneer Anomaly. Let me tell you about a tug that lasted 30 years. In the early 1970s, we launched two probes called Pioneer 10 and Pioneer 11. They were pioneers in the truest sense. The first machines to cross the asteroid belt, the first to see Jupiter and Saturn up close, and then the first to simply keep going, out past the planets, into the long emptiness. They are still out there now, silent, drifting. And as they drifted, something was wrong with the way they moved. We tracked them, year after year, by their radio signal, and the probes were slowing down. Now, that's expected. The sun's gravity is always tugging back on anything leaving the solar system. But the pioneers were slowing down a tiny bit more than the sun's gravity could account for. as if some faint, invisible hand were laid against them, gently pressing them back toward the sun. The size of it was almost absurdly small, about 8 times 10 to the minus 10 meters per second squared. Let me put that in human terms. It's roughly a 10 billionth of the gravity you feel standing on Earth right now. A whisper of a whisper. But it was steady. It was real. And it would not go away. And this is where it gets interesting, because for a while, this little anomaly was one of the most exciting numbers in physics. Think about what it could have meant. Maybe gravity itself behaves differently at the edge of the solar system. Maybe Newton was incomplete. Maybe Einstein was incomplete. Maybe there was a whole new chapter of physics hiding in the deceleration of 2 old probes. Serious people, good physicists, spent years chasing exactly that dream. Papers were written. Careers leaned on it. For 30 years, the pioneer anomaly sat there, unexplained, taunting. And then, in 2012, a physicist named Slava Turishev and his team finally closed the case. The answer was not a new force of nature. The answer was heat. The pioneers are powered by a lump of plutonium that runs warm. The electronics run warm, and all that heat has to go somewhere, radiating off the body of the spacecraft as infrared light. Here's the trick. The heat didn't leave evenly. A little more of it glowed off the front of the craft than the back. And light, even invisible heat light, carries a tiny push. So the probes were very gently shoving themselves backward, warmed by their own waste heat, pressed sunward by their own glow. When Turishev's team accounted for it properly, the anomaly vanished. In their words, once the thermal recoil force was included, no anomalous acceleration remained. And the final detail is the one I love. The effect slowly weakened over the decades, fading at exactly the rate the plutonium fuel decays. The probes were cooling, and the ghost cooled with them. So why am I telling you about a solved mystery in a video about the ones we can't explain? Because of what it teaches you. For 3 full decades, the smartest people in the field stared at this number and could not agree on what it was. The truth, when it came, was almost embarrassingly ordinary. Heat. But it took 30 years and a generation of doubt to say so out loud. And that should make you wonder about all the anomalies still sitting in the data right now. The ones we haven't solved yet. Some of them are probably waiting for their own boring answer, their own lump of warm plutonium. And some of them might not be. Number 8. The Arcade 2 radio hum. In 2006, NASA flew a balloon to the edge of the atmosphere. Hanging from it was an instrument with a long and very serious name that everybody just calls Arcade 2. Its job was simple to describe and fiendish to do. It was going to measure the temperature of the sky, not the air. The sky itself. The faint radio glow that fills all of space. You see, the universe hums. Everywhere you point a radio antenna, you pick up a low background of radio waves. Most of it we understand. Some of it is the afterglow of the Big Bang. Some of it is the combined whisper of billions of distant galaxies, each one a faint radio source, blurring together into a haze. We thought we knew how loud that haze should be. We'd added up all the galaxies, all the known sources, and we had a number. Arcade 2 went up, listened to the sky, and came back with a number that was far too big. The radio glow was roughly 6 times brighter than everything we know how to explain. 6 times. Not 6%. 6 times. It was as if you'd carefully counted every light bulb in a city, worked out how bright the skyline should be, and then looked up to find it blazing 6 times brighter than all those bulbs combined. And the obvious questions all led to dead ends. Was it our own galaxy's glow, not subtracted properly? They checked. It didn't fit. Was it the leftover light of the Big Bang behaving strangely? No, the spectrum was wrong for that. Was it some known population of galaxies we'd undercounted? That's the gentlest explanation, and it's still on the table. But to make it work, you have to invent a vast crowd of faint radio sources that nobody has ever actually seen. They'd have to be there, filling the sky, and yet invisible to every survey we've ever run. And then there are the stranger ideas. Because when something glows from everywhere at once and refuses every ordinary answer, physicists start to whisper about new physics. Some have proposed that the excess radio light is the death glow of dark matter. Particles quietly decaying all across the cosmos and releasing radio waves as they go. Others have pointed at relic neutrinos, ghost particles left over from the first second of the universe, decaying and shining. These are not crackpot ideas. They're in real journals, written by real cosmologists, because the alternative, a hidden ocean of invisible galaxies, is almost as strange. That was 16 years ago. The hum is still there. We've measured it again, and it hasn't gone away. And we still cannot tell you, with confidence, what is making the sky 6 times too loud. Space is supposed to be quiet. Mostly, it is. But underneath the quiet, there's a sound we can't place, coming from every direction, with no one willing to say what's making it. Number 7, the solar abundance crisis. Ask an astronomer what the sun is made of, and they'll answer without hesitating. Hydrogen, mostly, then helium, and then a thin seasoning of everything else, the carbon and oxygen and nitrogen and iron, the stuff astronomers lump together and call, slightly insultingly, metals. We've known this for a century. The sun is the most studied object in the sky. We have watched it every single day for longer than any of us have been alive. Surely, if there's one thing we know cold, it's the recipe of our own star. Here's the uncomfortable truth. We have 2 different ways of reading that recipe, and right now, they don't agree. The first way is spectroscopy. You take the sun's light, spread it into a rainbow, and read the dark lines printed across it. Each element leaves its own fingerprint in that rainbow, and from the depth of the lines, you can work out how much of each ingredient is present. For decades, this gave us a solid number for the sun's metal content. Then, in the 2000s, the technique got better. Much better. New models, accounting for the roiling, 3-dimensional churn of the sun's surface, more careful physics, sharper data. And the improved measurement came back lower. There was less carbon, less nitrogen, less oxygen than we'd thought. A cleaner, more modern number. Everyone should have been happy. Except for the second way of reading the sun. It's called helioseismology, and it is one of the most beautiful tricks in science. The sun rings. It vibrates like a struck bell, with sound waves rolling through its interior, and those vibrations show up as a faint shimmer on its surface that we can measure. By studying the exact pitch of the sun's ringing, we can map what's going on deep inside it, in regions no telescope will ever see directly. It's like working out the shape and contents of a bell purely from its tone. And helioseismology was adamant. The sun's ringing demanded the old, higher amount of metals. With the shiny new low number, the predictions broke. The speed of sound inside the sun came out wrong by about 1%. The depth of the great convective layer was off. The amount of helium near the surface was wrong by around 7%. None of it lined up anymore. So now, we have a genuine crisis, quietly sitting at the center of stellar physics. The better we measured the sun's surface, the worse our model of its interior became. Improve one, and you break the other. People have spent 20 years trying to reconcile them. A 2023 study looked at one of the most popular escape routes, simply allowing for more metals after all, and concluded, flatly, that higher metal abundances do not solve the solar problem. And here is why this matters more than it first sounds. The sun is our ruler. It's the standard we hold every other star against. When we say a distant star is young or old, hot or cool, rich or poor in elements, we are measuring it relative to the sun. If the model of the sun has a crack in it, that crack runs through every star in the sky. We orbit this thing. Our entire existence depends on it, and we cannot, at this moment, fully agree on what it's made of. Number 6. The faint young sun paradox. Let's stay with the sun, because the sun has another secret, and this one reaches all the way back to the beginning of life. Stars brighten as they age. It's not dramatic, it's slow, but it's relentless. Our sun has been getting steadily more luminous for its entire life, and it will keep doing so until, far in the future, it cooks the Earth. Run that backward, and you reach an unavoidable conclusion. The young sun was dimmer than it is today. A lot dimmer. About 4 billion years ago, when the Earth was new, the sun shone at roughly 70% of its current brightness. Now do the simple arithmetic. Take the warmth Earth gets today, knock it down to 70%, and you get a planet that should have been frozen. Not chilly. Frozen. A solid ball of ice. Oceans locked from pole to pole. The whole world a frostbitten white. Liquid water on the surface should have been impossible. And yet, we have rocks from that time. We can read them, and they tell us, without ambiguity, that there was liquid water on the early Earth. Rivers ran, oceans existed. Sediments settled in flowing water and hardened into stone we can hold today. And in that water, life was already getting started. The planet that should have been a snowball was warm and wet and alive. This is the faint young sun paradox, and it was first laid out in 1972 by two scientists, one of whom you've heard of, Carl Sagan, working with a colleague named George Mullen. And here's what I find remarkable. More than 50 years later, it is still not fully solved. Now, there's an obvious place to look for the answer: the greenhouse effect. If the early atmosphere trapped heat far more aggressively than today's, it could have kept the planet warm despite the feeble sun. Sagan's first guess was ammonia. That didn't last because sunlight tears ammonia apart in short order. The modern favorite is carbon dioxide, maybe with a helping of methane, a thick blanket of greenhouse gas wrapping the young Earth and holding in what little warmth the sun provided. It's a good answer. It might even be the right one. But here's the catch, the thing that keeps this in the unsolved pile. When geologists go and read the ancient soils, the minerals that formed in that early air, they put limits on how much carbon dioxide could actually have been present. And in a lot of studies, the amount the rocks allow is not quite enough to thaw the planet. Push the greenhouse hard enough to melt the ice, and you sometimes contradict the dirt. Trust the dirt, and the planet freezes again. So the paradox isn't that we have no answer. It's that no single, clean answer fits all the evidence at once. Every solution is a little too much in one place and a little too little in another. The story almost closes, and then it doesn't. And sit with what's actually at stake here. This isn't a distant quasar or an abstract number. This is the question of why the cradle of all life on Earth didn't freeze before life could begin. We are here. You are here, listening to this. And we cannot fully explain why the world was warm enough to let that happen. The sun was too faint. The water was there anyway. And in the gap between those two facts, somehow, is us. Number 5. The brightest explosion since the Big Bang. On the 9th of October, 2022, a wave of radiation washed over the Earth, and for a few seconds, it broke our instruments. It was a gamma ray burst. These are the most violent explosions in the known universe, the death cries of giant stars. When a star many times the mass of the sun runs out of fuel, its core collapses into a black hole in an instant, and the outer layers detonate. As the new black hole feeds, It fires two narrow jets of pure energy out from its poles at very nearly the speed of light. If one of those jets happens to be pointed at you, you get a gamma ray burst. For a brief moment, a single dying star can outshine everything else in the cosmos combined. We see these fairly often, scattered across the distant universe. But the one on that October morning was different. It was so bright that it saturated nearly every gamma ray detector in orbit. The instruments we built specifically to measure these explosions were overwhelmed, dazzled, unable to take it all in. Astronomers gave it a nickname that says everything. They called it the boat, the brightest of all time. And this thing was not next door. It came from a dying star roughly 2 billion light years away. That light, that radiation, had been traveling for 2 billion years before it reached us, and it still hit hard enough to blind our hardware. A burst this bright is the kind of thing we'd expect to see maybe once every 10,000 years. We happened to be watching when it came. But the headline brightness isn't even the strangest part. The strangest part came from a detector array high on a mountain in China called El Hasso. It caught the burst's highest energy light, and what it recorded should not have been possible. It saw photons with energies up to 18 tera-electron volts. You don't need to know what that unit means. Here's what you need to know. Photons that energetic, traveling across 2 billion light years of space, should not survive the trip. The universe is filled with a faint fog of low-energy light, the combined glow of every star that ever shone. And ultra-high energy gamma rays, plowing through that fog, are supposed to collide with it and be absorbed, snuffed out, long before they reach us. An 18 tera-electron volt photon crossing that distance and arriving intact is like firing a bullet through a mile of fog and having it come out the other side without slowing down. So, how did it get here? The careful, mainstream answer is that a perfectly aimed, very narrow jet, plus some reasonable assumptions about that cosmic fog, can just barely make the numbers work. Probably. But this event was so extreme that serious physicists wrote serious papers asking whether something else was going on. Whether those photons survived by briefly turning into a hypothetical particle, an axion, a ghost that doesn't feel the fog, and then turning back. Whether the burst was quietly testing the very rule that says nothing outruns light. Most likely, the universe found an ordinary way to do an extraordinary thing. That's usually how it goes. But for a few seconds on an October morning, the death of a star 2 billion years ago reached across all that emptiness, blinded everything we'd built to watch it, and sent us light that, by our own rules, should never have arrived. And we are still arguing about how. Number 4, the Great Quasar Alignment. I want you to picture the early universe. Not stars, not yet planets. Picture quasars. A quasar is a supermassive black hole at the heart of a young galaxy, feeding so greedily that the matter spiraling into it blazes brighter than the entire galaxy around it. They are the brightest steady objects in all of creation, beacons we can see from the far edge of the observable universe. Each one spins. Each one has an axis, like a top, a direction its whole engine is oriented around. Now, those axes should point every which way. Randomly. Why wouldn't they? You've got quasars scattered across billions of light years, in different galaxies, in different regions of space, that have never had anything to do with one another. There is no reason on Earth, or off it, for one quasar's spin to care about another's. Toss a billion spinning tops across a continent, and they'll land facing in every possible direction. That's just common sense. Common sense, it turns out, is wrong. In the late 1990s, a Belgian astronomer named Damien Hutsemakers started noticing something strange in the light from quasars. He was measuring their polarization, the orientation of their light waves, which tells you something about how the quasar is tilted. And the polarizations weren't random. Across enormous stretches of sky, billions of light years, they seemed to be lining up. He kept at it for years, with better and better data, using the Very Large Telescope in Chile, and the picture sharpened instead of dissolving. Quasars that belong to the same vast cosmic structures, strung along the same threads of the cosmic web, have spin axes that align with those structures. Parallel, or neatly perpendicular, but not random. When he ran the numbers, the odds of this happening by chance came out at around 1%. And later work found the same alignment in the quasar's radio emission too. It wasn't a fluke of one measurement. It held up. Now sit with the scale of this. These quasars are separated by distances so vast that light itself, the fastest thing there is, could not have crossed between them in the entire age of the universe. They are, in the most literal sense, beyond each other's reach. Nothing one quasar does could ever have influenced another. They could never have agreed on anything. And yet, somehow, their spins seem coordinated, as if some giant comb was drawn through the young cosmos, lining them all up before they ever lit. What is that? Honestly, we don't know. The cautious explanation is that the cosmic web itself, the gravity of the great filaments of matter, gently torqued these galaxies as they formed, nudging their spins into alignment. That's plausible, and it doesn't require anything new. But it has to work across distances that feel impossible, and the sample is small enough that some researchers still suspect a subtle bias is fooling us. But if it's real, and it has been seen more than once now, then it's a hint that the universe has a structure to it, an orientation, a grain to the wood, at scales we have no comfortable way to explain. The black holes were combed, and nobody can tell you what holds the comb. Number 3, cosmic birefringence. This one is subtle, and it might be the most important thing on this entire list. Stay with me, because the payoff is enormous. There is a light that fills the whole sky. It's the oldest light there is, released about 380,000 years after the Big Bang, when the young universe finally cooled enough to become transparent. We call it the cosmic microwave background, and it is, in a real sense, a baby photograph of everything. It has been traveling, untouched, for more than 13 billion years, soaking through all of space, reaching us from every direction at once. That ancient light is polarized. Its waves are oriented in particular directions, set down at the moment it was born. And here's the key idea. As that light traveled across 13 billion years of empty space, its polarization should not have changed. Empty space is supposed to be neutral. It shouldn't twist light. The orientation the light had when it left should be the orientation it has when it arrives. That's just how a vacuum is meant to behave. In 2020, two physicists, Yuto Minami and Eiichiro Komatsu, found a clever way to check. The problem had always been that you don't know exactly how your own instrument is rotated, so you can't tell a real twist in the light from a tiny tilt in your detector. Their trick was to use the dust in our own galaxy as a reference. Galactic dust glows, and its glow is affected only by your instrument's tilt, not by anything that happened to the ancient light on its long journey. So if you compare the two, you can separate the instrument's error from a real, genuine rotation of the cosmic light. They ran it on the best data we had. And they found a twist. The number was tiny, about 1/3 of 1 degree. The oldest light in the universe appeared to have been gently rotated by a fraction of a degree on its way to us. And I need you to understand that in standard physics, there is nowhere to put that number. A vacuum doesn't do this. For the polarization of light to rotate uniformly across the whole sky, something has to fill all of space, an invisible field woven through every cubic centimeter of the cosmos, quietly turning the plane of light as it passes. And we have a name for things like that, a field filling all of space that we cannot see directly. That is exactly the kind of thing dark matter or dark energy might be. The leading candidate is a so-called axion-like field, a faint, parity-violating presence that would gently rotate light precisely the way this signal suggests. If this measurement is real, that tiny twist is the first direct fingerprint of the dark sector, the invisible 95% of the universe we have never been able to touch. So why isn't this the biggest story in science? Because of one honest, deflating number. The signal sits at about 2.4 sigma. In physics, that's a hint, not a discovery. It's the level where you lean forward, not the level where you celebrate. And the thing that could fake it, a tiny miscalibration of the instrument, is exactly the kind of gremlin that's hard to rule out completely. So we wait. Better telescopes are looking right now, trying to push that number higher, or watch it melt away. And somewhere out there, the oldest light in existence keeps arriving, very slightly turned, carrying what might be a message from the dark half of the universe, written in an angle smaller than the width of a fingernail held at arm's length. We just can't be sure yet that anyone wrote it. Number 2. The big ring in the sky. There is a rule at the very heart of cosmology. It's so fundamental that most of modern astronomy is quietly built on top of it, and it's called the cosmological principle. It says something that sounds humble and obvious. On the largest scales, the universe is the same everywhere. Smooth, uniform. Look in any direction, zoom out far enough, and you should see roughly the same thing, the same even scattering of galaxies, with no special places and no grand designs. The universe, at the biggest scale, is supposed to be boring, featureless. The same soup, stirred evenly. That rule sets a limit. There's a maximum size that any single structure in the universe is allowed to be. The biggest clump of stuff, gravity, could have plausibly assembled in the time available. It works out to a bit over 1 billion light years. Nothing should be bigger than that. Go beyond it, and you're not looking at a structure anymore. You're looking at the smooth, even background. In 2021, a PhD student named Alexia Lopez at a university in England found something bigger. She called it the giant arc. It's a sweeping curve of galaxies and gas, traced out across the distant sky, and it stretches about 3.3 billion light years from end to end. That is several times larger than the supposed limit, a structure that, according to the rule, should not be able to exist. It made headlines. It raised eyebrows, and plenty of cosmologists said, reasonably, the eye loves to find patterns. Let's see if it holds up. And then, 2 years later, Lopez found another one. This time, it was a ring. The Big Ring, she called it, plainly enough. A vast circle of galaxies and clusters, about 1.3 billion light years across, with a circumference of some 4 billion light years. And here's the detail that lifts the hair on the back of your neck. The Big Ring and the giant arc are not in opposite corners of the sky. They are practically neighbors. They sit at the same distance from us, which means we're seeing them at the same moment in cosmic history, and they're only about 12 degrees apart in the sky. Two impossible structures, side by side, in the same patch of the early universe. And the ring is not a messy blob. When her team studied it, the shape suggested it might actually be a coil, a corkscrew, that just happens to look like a ring because we're seeing it face on. Think about that. Random matter, scattered by gravity, does not arrange itself into rings and coils 1 billion light years wide. Rings are ordered. Rings look designed, even when they aren't. And we have no accepted mechanism, none, that builds a thing like this. Now, the careful voice in the room says these could still be statistical illusions, chance alignments of background objects that our pattern-hungry brains are stitching into shapes. That's a real possibility, and Lopez knows it, which is why her team ran the significance tests and argued the structures are real. But the wider field has not fully accepted that the cosmological principle is broken. Not yet. But here's where it stands. The rule says the universe should be smooth and featureless at these scales. And out there, at the same distance, 12 degrees apart, are an arc the size of a nightmare and a ring that might be a coil found by the same person, 2 years apart, both too big to be allowed. The universe was supposed to be boring at the largest scale. Somebody forgot to tell the universe. Number 1. The cosmic dipole crisis. We've arrived at the one that, if it's real, quietly pulls the floor out from under everything else. Let me take you back to that rule from a moment ago, the cosmological principle. The universe, on the largest scales, looks the same in every direction. We don't just hope this is true. We need it to be true. Almost every number we quote about the cosmos, its age, its expansion rate, the amount of dark matter and dark energy, all of it is calculated, assuming the universe is, on average, the same whichever way you look. It is the bedrock. It is the assumption underneath the assumptions. There's a clean way to test it. Imagine counting the most distant objects in the universe. Quasars, those blazing young black holes, spread across the entire sky. If the universe is truly uniform, you should count roughly the same number in every direction. There's one allowed exception. We're moving. Our galaxy is drifting through the cosmos at a certain speed, and that motion should make the sky appear very slightly crowded in the direction we're heading, and very slightly sparse behind us, the same way rain seems to come at your windshield more from the front when you drive. That effect is small, and crucially, we can calculate exactly how big it should be, because we already know our speed. We read it, decades ago, from the faint motion shift baked into that ancient background light. So here's the test. Count the quasars across the sky, measure how lopsided the count is, and check whether the lopsidedness matches the small amount our motion allows. In 2021, a team led by Nathan Seacrest did exactly that. They built a catalog of nearly 1.4 million quasars, covering most of the sky. They measured the lopsidedness, and it was too big, not a little too big. The imbalance they found was about 2.7 times larger than our motion can explain. Almost 3 times too much. And the statistical strength of it is what makes this so hard to wave away. Physicists have a threshold for calling something a discovery. They call it 5 sigma, a level where the odds of it being a random fluke are about 1 in 3.5 million. The quasar dipole came in at 5.7 sigma. Past the line, over the threshold, we normally reserve for announcing that something is real. So now, you're trapped between 2 doors, and you don't like what's behind either of them. Door 1. The lopsidedness really is just our motion, which means we are moving through the universe almost 3 times faster than we thought, fast enough to break our other measurements. Door 2. The lopsidedness is not our motion. It's the universe itself being genuinely uneven, lopsided, different in one direction than another, on the very largest scale. And that would mean the cosmological principle, the bedrock, the assumption under everything is wrong. Either way, something we were sure of isn't true. Now, I'll give you the honest counterweight, because you deserve it. Many cosmologists think there's a quieter answer hiding here. That when you count distant quasars, subtle effects, the way galaxies clump together, the way these objects change over cosmic time, the precise quirks of your catalog can fake a dipole that looks too big without anything being fundamentally wrong. People are working on exactly this right now, re-examining the data. And the argument is genuinely unsettled. This is not a closed case. It's a live wire. But step back and feel the shape of it. We built the entire edifice of modern cosmology on the idea that the universe has no preferred direction, No special axis, no grain. And when we went to check that idea, in the most direct way we know how, by simply counting the lights in the sky, the count came back crooked, past the discovery threshold, pointing, unnervingly, in roughly the same direction as that ancient background light we'd always trusted. Maybe it's a trick of the data. Maybe it's the most important crack we've ever found. We genuinely do not yet know which. And that's the strange, humbling place we actually live in. We have mapped the universe back almost to its first moment of light. We have weighed galaxies we will never visit and timed the decay of stars that died before the Earth was born. And yet, the deepest question, whether the cosmos has a direction, whether the ground beneath all our certainty is level or tilted, is still open. We are standing on the foundation, looking down, watching a crack, not yet sure if it's a flaw in the stone or just a shadow. We built our whole map of everything on the promise that no direction is special. The universe has not yet told us whether that promise was ever true. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.